Alright, so we just look at the DC bias circuit and need some calculation for bias stability. RB equals beta RB over 10, and beta was equal to 100, and these were the value of RE equals 15 kilo ohms, and we find VVB equals RB over 1 minus VBB over VCC. We plug in values, we get 82.9, and we chose for standard value R1 equals 82 kilo ohms and RB equals 18 kilo ohms. Now we're looking at the emitter follow base injection bias, and very often we're required to design an amplifier which are not concerned with the Q point changes with beta. Yeah? We're not concerned with the Q point changes with beta variation due to VCC or due to the transistor replacement. So here we're going to do the emitter follower with the base injection bias. Kilo ohms there, 1.5 kilo ohms. And base and emitter, and VCC equals 20 ohms. Plus, minus, yeah. And we're going to take a look, looking at from A prime to A. Now in this case, the base bias resistor R1 shown in the previous figure that you wrote out can be illuminated, and the above figure showed that the emitter follower of the previous figure with R1 removed. And this is called the base injection bias, when we remove I1, R1. Well, let us find R2 so that V2 can undergo a maximum symmetrical swing. So we're going to remove R1, and this is called the base injection bias, and we're going to find R2 so that V2 can be undergo a maximum symmetrical swing, or the V low. Now for this method we find the Thevenin's equivalent circuit looking into the base at A. So we're going to do the Thevenin equivalent circuit looking into the base of A prime. So applying KVL now. On the application of Kirchhoff voltage law, this will yield now that VB is equal to VE I is equal to 7 plus 1 plus beta I base. All the circuits you'll really one plus beta R. This is the equivalent circuit looking into the base terminal. This is the equivalent circuit looking into the base terminal. And the DC portion of the emitter follower would be A. i.e. A and A prime. So we're looking into the section A prime, and this will be base. And we could also draw complete DC equivalent circuits. So we have a complete DC equivalent circuit. beta. This is a complete equivalent circuit for the DC, for the base injection bias, in which R1 is removed. So we are left with R2. This is C 10 to input VI. Base injection bias. Now in the second example, we have now that VCC was equal to 21 volts. V and beta equal 100. So with these values, VCC equals 21 volts, RE equals 1500 ohm, and beta is equal to 100. We calculate R2. Let's write R2 right in this section. From the value that I'm equal to 21 minus 15.7 over 10 equal to 53 kilo ohms. Yes, if we plug in these values, VCC is 21 volts, VC equals 50.7 volts, R equals 1500 ohms, beta equals 100. We get now that R2 is equal to VCC minus VBQ. I know that IBQ, let's look for IBQ. IBQ equals to VE over R, the 1 plus beta, is equal to 15 over 1500 and 101. So 1 plus beta, beta being equal to 100, this would be now 101. And that would be approximately be equal to 1 100 microvolts. For this, we see that standard value of 56 ohm is used in practice. A standard value of 56 ohms, or 56 kilo ohms standard. That's used in practice. Here we calculate it to be 53 kilo ohms, but in practice, standard value of 56 kilo ohms is used. Let's calculate VBQ. We say that VQ we plug in the values here again, we get that as equal to 12 volts. So instead of 15 volts, the maximum peak to peak symmetrical swing under this condition will be reduced accordingly. So we're expecting 15 volts instead of 15 volts, right? The maximum symmetrical peak swing is reduced to 12 volts according to this calculation. And it is reduced accordingly. So E is equal to RE, the 1 plus beta. And for this one, a much larger resistance is obtained from this one. Whereas for this one, RB, much smaller resistance is obtained. And we'll consider this when we're doing small signal analysis circuit conditions. All right, we want to